Kylo Limit Loren here, talking to you about how to find limits that fail to exist. Why did Anakin cross the road? To get to the dark side.
First vocabulary term is a limit. That would be the value that a function or sequence approaches as the input or index approaches some value. So for part A, we have a sequence where we're starting with A and then each number is multiplied by half or divided by 2. And if you were to continue doing that, you would keep getting smaller and smaller numbers that would approach 0 but never quite get there, which means that the limit of this particular sequence would be 0. When we had a function, the limit was equal to the value that the function approaches as the input or index approaches some value. So the input or index we said was the x value, and if we pick a particular x value and look at the function as it approaches that x value, we want to see what y value it approaches as x approaches that particular value. And you can see as x approaches 2, this function approaches a y value of 4. Therefore, the limit of f of x as x approaches 2 would be equal to 4. For part C, you can see that as x approaches 3 for this particular function, it's different on either side. As x approaches 3 from the left, your function approaches negative infinity. As x approaches 3 from the right side, your function approaches positive infinity. Therefore, the limit does not exist here. And technically, even if they were both going to positive infinity or both going to negative infinity, you could say that the limit does not exist, because when your limit is equal to infinity or negative infinity, it technically does not exist. And we'll talk about that later. Second vocabulary term is oscillate. So in math, that would be a function whose output values move back and forth, tending to no limit. So here we have cosine of 1 over x, and you can see that it oscillates between 1 and negative 1, and it doesn't get any closer to a particular y value as it gets closer and closer to 0. It actually just keeps bouncing back and forth, meaning that it technically does not have a limit as x approaches 0. Same thing with sine of 1 over x. You could see that as x approaches 0 for this particular function, the y values keep oscillating back and forth between 1 and negative 1. Therefore, there is no particular limit of sine of 1 over x as x approaches 0. You would say the limit does not exist. Now let's talk about some common types of behavior associated with the non-existence of a limit. So if we have the limit as x approaches c of f of x equals L, the first type of behavior that would require the limit to not exist would be f of x approaches a different number from the right side of c than it does from the left side of c. And this makes sense, right? You can't have the limit as x approaches c of your particular function equal a number if it's approaching two different y values from the left and the right. Second, we have f of x increases or decreases without bound as x approaches c. And we talked about this a little bit earlier. If you have a function that approaches positive infinity from both sides or negative infinity from both sides, you would technically say that the limit does not exist, because infinity is not a particular number, L. It's infinity. It goes on forever. 3, we have f of x oscillates between two fixed values as x approaches c. And we talked about this when we were talking about the definition of oscillate. We looked at cosine of 1 over x and sine of 1 over x, and we saw that it bounced back and forth between 1 and negative 1. And because it doesn't approach any particular y value, it keeps bouncing back and forth, the limit does not exist. And 4, we have c is not in the domain of f of x. So this would be, let's say if you have a radical function, y equals the square root of x. If you were to say the limit as x approaches negative 5 of that particular function, you would not be able to find that limit because negative 5 would not be in the domain of the square root of x. It starts at 0 and continues on in a positive manner.
Time to use the force. It's example time.
Now example 1 says complete the table and use the result to estimate the limit. Use a graphing utility to graph the function to confirm your results. So here we have the limit as x approaches 0 of this particular function right here. And again, we're taking the limit as x approaches 0. So in our table, we're picking 3 x values to the left of 0 and 3 x values to the right of 0. We do that because we want to make sure that it's approaching the same y value from both sides as x approaches 0. That way we could say that definitely the limit exists at a particular y value. So what we're going to do then is plug in negative 1 for our x here and get the y value that goes with that. We then take negative 0.1, plug it in for x here, and get the y value that goes with that. Plug in negative 0.01 for x here, and get the y value that goes with that. So we can see that from the left side, it's looking that as x approaches 0 from the left, our y value is approaching 2. Let's hope that it approaches 2 from the right, and then we can say that the limit as x approaches 0 is equal to 2. So we plug in 1 here, and we end up getting 0.5379. We plug in 0.1 here for x, and we get the y value that goes with that. Plug in 0.01 here for x, and we get the y value that goes with that. So these values look like they are approaching 0 from the right. So as x approaches 0 from the left, your y value is approaching 2. As x approaches 0 from the right, your y value is approaching 0. Therefore, the limit does not exist because it's approaching two different numbers from the left and the right. You can confirm this with your graphing calculator. If you were to graph this, you could see that from the left side, your function is approaching a y value of 2 as x approaches 0. And then from the right side, your function is approaching a y value of 0 as x approaches 0 from the right. Now part B, we're doing the same thing. We're taking the limit as x approaches 0, this time of cosine of 1 over x. So again, we're picking 3 x values to the left and 3 x values to the right of 0 because that's what x is approaching. And we're going to see if f of x approaches some value from both sides. Therefore, we can have a limit. So we're going to plug in negative 1 over pi for x here and get the y value that goes with that. Take negative 1 over 2 pi, plug it in for x here. Get the y value that goes with that. Take negative 1 over 3 pi, again plug it in, get the y value that goes with that. Do the same thing on the other side. We're plugging in each of these values for x and getting the y value that goes with it. Now, if you recall, we looked at the graph of this earlier, and it oscillates. It bounces back and forth between 1 and negative 1, and we see that our table confirms that. As x approaches 0 from the left, we are bouncing back and forth between 1 and negative 1. As x approaches 0 from the right, same thing. It bounces back and forth between 1 and negative 1. Therefore, the limit as x approaches 0 of cosine of 1 over x does not exist because f of x oscillates between 1 and negative 1. Now we can confirm this with our graphic calculator. We saw this earlier. As x approaches 0, you can see that the function just keeps bouncing back and forth between 1 and negative 1 and doesn't approach any given value.
You try.
Okay, we're doing the same thing. Here, we pick 3 x values to the left of 0, 3 x values to the right of 0. We're plugging these in for x and getting the y value that goes with them. Plug in this guy for x, get the y value that goes with that. Plug in this for x, y value that goes with that. Same thing on the other side. If I were to plug in 1, 0.1, and 0.01, I get the y value that goes with those. And you can see that as x approaches 0 from the left, it looks like f of x is approaching infinity. As x approaches 0 from the right, f of x is also approaching infinity. So later on, we're going to have you say that the limit as x approaches 0 of 1 over x squared would equal infinity. But for now, we're just saying that the limit does not exist because f of x increases without bound. We confirm this with our graph calculator. You can see that as x approaches 0 from the left and the right, you are going towards infinity. Therefore, the limit does not exist. For part B, we're doing the same thing. We have the limit as x approaches 2 of the square root of x minus 5. So I'm going to pick 3 x values to the left of 2, 3 x values to the right of 2, and plug them into our function and see what y values I get with those. So if I were to plug in negative 1 for x, negative 1 minus 5 is negative 6, and the square root of negative 6 is an imaginary number. Same thing when I plug in 0. 0 minus 5 is negative 5. The square root of negative 5 is an imaginary number. Plug in 1. 1 minus 5 is negative 4. Square root of negative 4 is an imaginary number. If I were to plug in 5, 5 minus 5 gives me 0. Square root of 0 is 0. If I were to plug in 4, 4 minus 5 is negative 1. Square root of negative 1 is imaginary. Same thing with 3. Square root of negative 2 is imaginary. So you can see that x is equal to 2 is not part of the domain of this particular function. Because of that, you can say that the limit as x approaches 2 of the square root of x minus 5 does not exist because c is not in the domain of f of x. You can confirm this with your graphic calculator and see that x equals 2 is right here and it's not part of the domain of this particular function. Example 2 says use the graph to find the limit if it exists. If the limit does not exist, explain why. So we have the limit as x approaches 0 of 1 over x. You can see that as x approaches 0 from the left side, your y value approaches negative infinity. As x approaches 0 from the right side, your y value approaches positive infinity. Now, because these approach two different infinities, you could say that the limit as x approaches 0 of 1 over x does not exist. And for right now, even if they did both approach positive infinity or both approach negative infinity, we would say that the limit does not exist. Later on, we're going to eventually, if they go towards the same infinity, we're going to specify that. We're going to say that the limit would equal positive infinity or negative infinity. Now, let's look at part B. We have the limit as x approaches 0 of the square root of x minus 1 plus 2. And you can see that as x approaches 0, it's not even part of that particular function. It's not part of the domain of that function. So we can say that this limit also does not exist. And that is because, again, your c value, 0, is not part of the domain of this function. It starts at x equals 1 and continues on in the positive direction. There is no x equals 0 for this function.
You try.
Okay, we're finding the limit as x approaches 1 of f of x, and f of x is a piecewise function. F of x equals -8 when x is less than 0, that would be this portion right here. And f of x is equal to x squared when x is greater than or equal to 0, so that would be this part right here. Now don't let this confuse you. It's asking for the limit as x approaches 1, not the limit as x approaches 0. If it were asking for the limit as x approaches 0, it would be approaching two different values from the left and from the right. But because it's asking for the limit as x approaches 1, you can see that as x approaches 1 from the left, you're approaching a y value of 1. And as x approaches 1 from the right, you're also approaching a y value of 1. Therefore, you could say that the limit as x approaches 1 of f of x is equal to 1. Now the limit as x approaches 0 of 1 over sine x, we talked about this earlier, because this function oscillates between 1 and -1 as x approaches 0 from the left and the right, you could say that this limit does not exist. And again, because your function oscillates back and forth between 1 and -1 as x approaches 0. Example 3 says use the graph of the function f to decide whether the value of the given quantity exists. If it does, find it. If not, explain why. So here, f of 1. This is just asking you what is the y value of this function when x equals 1. So we look over here. Our function when x equals 1 has a y value of 2. That's where the hole is filled in. This is open, so it doesn't exist. This is open, so it doesn't exist. Here is where our y value exists. So we would have 1, 2 would be our point. So f of 1 is equal to 2. The limit as x approaches 0 of f of x. So let's look. As x approaches 0 from the left, we are approaching a y value of 2. As x approaches 0 from the right, we are also approaching a y value of 2. Therefore, the limit as x approaches 0 of f of x is equal to 2. The limit as x approaches 1 of f of x. So here, as x approaches 1 from the left, our y value is approaching -1. As x approaches 1 from the right, our y value is approaching 0. Therefore, you could say that the limit does not exist because it approaches two different values from the left and from the right. Now we have the limit as x approaches 3 of f of x. So we look over here, 3 is right here. So as x approaches 3 from the left, we're approaching a y value of 0. As x approaches 3 from the right, we're approaching a y value of 1. Therefore, the limit also does not exist because it's approaching two different y values as x approaches 3.
I wonder how hot this... Oh, you try.
Okay, we're doing the same thing here. F of -4 is asking what does the function equal when x is equal to -4. So what's the y value of the function when x is equal to -4? Where's the point filled in? It's right here. So when x is equal to -4, your y value of that function would be 3. Now the limit as x approaches -4 of f of x, that's going to be different. As x approaches -4 from the left, it looks like your function is approaching a y value of 3. As x approaches -4 from the right, your function is approaching a y value of -2. Therefore, the limit as x approaches -4 does not exist because it approaches two different y values from the left and from the right. Now we have the limit as x approaches -1 of f of x. So we look at -1 is right here. As x approaches -1 from the left, we're approaching a y value of 4. As x approaches -1 from the right, we're also approaching a y value of 4. Therefore, you can say the limit as x approaches -1 of f of x is equal to 4. Now let's look at the limit as x approaches 4 of f of x. So x equals 4 is right here. As x approaches 4 from the left, you can see that the function is approaching a y value of 2. As x approaches 4 from the right, the function is also approaching a y value of 2. Therefore, you could say that the limit as x approaches 4 of f of x is equal to 2. Now, don't forget, the limit as x approaches some number, it doesn't matter whether the point is filled in or not, whether the point exists or does not. We are concerned with what happens around it, what it's approaching from the left and the right. It doesn't matter what it actually is at that particular value. Now example 4 says sketch the graph of f, then identify the values of c for which the limit as x approaches c of f of x exists. So we're going to sketch this graph real quick. It's a piecewise function. We have f of x is equal to 0 when x is less than or equal to -6. f of x is equal to 2x plus 9 for negative 6 less than x, which is less than 0. And then we have f of x is equal to negative 1/2 x plus 4 when x is greater than or equal to 0. Now what we need to do is determine the values of c for which the limit as x approaches c of f of x exists. Well, it's just not going to exist anywhere where the limit from the left and from the right are not equal. So that would be at x is equal to negative 6 and x is equal to 0. We would have limits that do not exist because they approach different numbers from the left than they do from the right. So you can say that the limit as x approaches c of f of x exists for all values of c not equal to negative 6 or 0. Okay, example 5 says sketch the graph of the function f that satisfies the given values. There are many correct answers. So here's the deal. I'm going to graph what I think the solution would be. Your graph may look a little bit different, but some of these things in my graph will need to be on your graph. Let's check this out. It says f of 1 is undefined. So you look over here, that means that at x is equal to 1, your function is either going to have a whole or an asymptote. Let's keep reading to figure out which one. It says the limit as x approaches 1 of our function has to equal 4. Because the limit as x approaches 1 exists for this particular function, that means it's going to be a whole, not an asymptote. If it was an asymptote, the limit would be infinity or negative infinity or non-existent. So what we do then is we put a whole at x is equal to 1. Now where on the graph? Well, since the limit as x approaches 1 of f of x equals 4, we know that we're going to have to put a whole at 1, 4. And then we'll just draw our function leading up to that whole on either side. Next, it says the limit as x approaches 8 of our function has to equal negative 1. So at 8, negative 1, we are then either going to have to put a whole or a point. We don't quite know yet. Read the next piece of information. It says f of 8 has to equal 3. That means that there must be a point at 8, 3 right here. So I have to put a point here, and because it's a function, I can't have a point here and a point here. I have to put a point here and then a hole here. So it's going to look something like this. Now what I do is I connect the holes either with straight lines or with curved lines, however you want to do it. This is now a function which has f of 1 undefined. It has the limit as x approaches 1 of our function equal to 4. The limit as x approaches 8 of our function equals negative 1. And f of 8 also equals 3. That's how you do that.